E+A. That's the point. Yes. So the point of my talk is indeed to introduce these E+A galaxies, and then from there we'll learn about like machine stuff, which I learned this summer from the students, which I was very, very happy with. But this is one piece, the latest incarnation of a series of work on E+A galaxies has been going on for 4 or 5 years now, with a whole bunch of students. A couple of them here, right here. Maddie Chang from Cornell's right over there, and Leah Voytovich from Penn is the person who's going to give the second half or the better part of this talk. And then just so many people have gone through here, and it's been a real pleasure, and have all these institutions being involved in helping to make this all work out so successfully. And I just want to continue that point and say that as a shameless plug, feel free to read it while I talk. I'm not going to read the slide itself, but this all came from this REU program and then everything else that's come after it for all these years. Now, you heard, I think Jay was saying that right now, in fact, this weekend is at Vassar College, this KMAC REU program symposium that they're having now. And indeed, there are a lot of REU programs in New York State. There's one at the New York City AMNH that we have there that's funded primarily by the National Science Foundation, but also by Sloan and by NASA. There's one at Cornell as well. There is one elsewhere. RIT, that's right. So please, everybody, look around, apply, and consider these. This has been tremendous for me, and to get scientists and a number of them now going on to graduate school and doing great work. So by all means, if you have any questions, please ask all the different institutions about how to apply for REUs and do that. And especially consider the New York City thing if you're upstate, because New York, right? Okay, so talking about E+A galaxies, what are they? Well, Alan Dressler and Jim Gunn back in 1983 took spectra of unusually blue galaxies in clusters of galaxies at redshifts of several tenths. They were called Butcher-Ohmler clusters, right, Rose? Yeah, we worked on those in graduate school. But anyway, Dressler and Gunn noticed that there were a bunch of these blue galaxies that were elliptical galaxy looking because they had no emission lines indicating star formation, but they had unusually strong A-star absorption spectra, that is hydrogen-Balmer lines, H beta, H gamma, H delta, and so forth. So they were nicknamed E+A galaxies because we didn't know what they were. It looked like that they were just elliptical galaxies with a bunch of A-stars stuck in them. Over time, people worked on them a little bit more. Rob Kennicott and I looked at some mergers in the nearby universe and compared them to the spectra and characteristics and say, hey, these are pretty darn similar. Is it that some starburst happened and then post-starburst going on from there? Richard Green and I did some very early elementary spectral synthesis of these galaxies and showed that indeed they could be modeled very simply by an early type spheroidal galaxy stellar population plus a whole bunch of A-stars, or stars that were about 1 billion years old. So going on from there, a lot of people started working on these, but they're very rare. So it was almost like mere curiosities, people looking at them. They were interesting, but you weren't going to stake an entire career's worth of work on them because there weren't enough of them, right? So Anne Zabludoff, Stefan Charlot, Nelson Caldwell, Jim Rose, Andy Barger, Bianca Poggianti, blah, 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 did all this. But sort of just did it sort of as on the side. But now we have spectra of millions of galaxies, thanks to Sloan and many other things. And now there are enough E+A galaxies that we realize that they are an important, say, evolutionary stage between what we might call the blue sequence, star-forming galaxies, blue cloud, and the red sequence, which are the quiescent, quenched galaxies. So a lot of people that I've listed here, for example, are starting to look at these galaxies and say, wow, these aren't just mere curiosities, but they have a lot of things that they can tell us about how galaxies evolve from blue to red. And some of them are forming stars, some of them aren't, some of them are old, some of them are new, some of them are older, some of them newer. So, how are we going to really study them with great care and figure out how to place them in a way, a sequence, shall we say, evolutionary, if one exists at all. So we want to compare apples to apples, and we're not sure that we are. So this is my favorite E+A galaxy in the universe. This was discovered by Ogerle, Hill, and Hessel in 1991, serendipitously. But if you can take a look at the spectra, you see that it's wrong, right? The classification of this galaxy is as a redshift 0.2 galaxy, and all the marks of the lines are wrong. It indicates just how difficult these galaxies are to find and identify automatically. The Sloan algorithm failed miserably in figuring out what they were. But if we can see, there is no H-alpha emission up here. Those two lines are not nearly helium-1, but those are actually nitrogen-2. They bracket the H-alpha. There's no H-alpha in the middle. And then you see H-beta, gamma, delta, epsilon, eta, zeta, theta, etc. Right? All the way down, just as if it were a textbook A star. But it's not. It's actually a galaxy. Now this little plot over here shows that this greenish dotted line is, if you just put a regular solar metallicity 1 billion-year-old stellar population right on top of the spectral energy distribution, it just about fits perfectly. Right? And if you look at this image, the reason Dave Thompson at Caltech decided to nickname this object flagellum is because it looks like it has a little flagellum in the back. Right? It looks like one of those eugleninas that you used to see paramecium eat. When you were looking in biology class and so forth. So he calls it flagellum. Anyway, it's a really cool object, and this is the kind of thing that we're trying to study and understand, and realize just how many there are in the universe and what kind of role they play. So what we want to do in these past few years was to leverage, go beyond what we used to know, just individual single spectra of individual spots of galaxies, and try to look at integral field spectra, IFS, where you use fiber optics to get a whole spatially resolved spectrum across an entire galaxy face to understand what these things are. And wow, they're all number one. How did that happen? Okay. The four criteria are, number one, notice that the light blue continuum, right? It's kind of light blue, not super blue like a, say, starburst galaxy, but it's actually bluish. So that's one. And then number one, you see that there's DN4000. That's the splitting between between this part of the spectrum and that part of the spectrum. See how large the continuum difference. Oh, thank you. Yeah. See, that's why she's a AAS board member. So we got this here. And you notice that there's a big difference between this part of the spectrum and that part. So we want to measure that. That's called DN4000. And then number one, we want to make sure that there's no H-alpha emission and only a little bit of oxygen too. So there's no ongoing star formation that we see through nebular emission lines. So there's no H-alpha in between these nitrogen 2 lines, and there's no oxygen 2 here either. It might be something very weak, but it's not, this definitely star forming. And then finally, number one, we want to make sure that they have strong Balmer absorption lines of equivalent width at least 3 angstroms. And those are these, right? Beta, H gamma, H delta, H epsilon, et cetera, et cetera, et cetera. So those are like 4, say, principal components, shall we say, or deterministic factors, or all of them obviously equally important in determining what an E+A galaxy is actually about. So the MANGA project, which is one of the 4th generation Sloan Digital Sky Survey projects, used fiber optics, put them in hexagons, and then placed them on galaxies. There are 8,000 of them have been observed this way so far. The total number should be around 10,000, so all the observations should be finished in about a year, data processing in about 2 years. And we're very fortunate to be part of that process, so we've had a whole bunch of students work on this over the years. As they've come about, we've tried to use things like single fiber spectra selection here to try to find an E+A galaxy and look at both its specific spectroscopic and its more sort of fit continuum type structures. And then here is some of the spatially resolved maps from MANGA of some of these E+A galaxies, all the different things, diagnostics, which aren't that important right now in our description of what they are. Here's another thing about whether or not you're using the width of the H-alpha equivalent widths and the nitrogen 2 and the log of the flux of the H-alpha line to try to see if you can measure whether how many of these spaxels, we call them, are made of old stars or look like AGN or look like star-forming spaxels. So using all these different techniques, we try to find some reasonable way, including summing all the spaxels together to form a single spectrum, compare them to individual, say, the spectrum from the center aperture or something, to figure out whether these are E+A galaxies or not, what kind they are, how old they are, and how they've been evolving and how they may evolve over time. So this is the last slide that has any content in it where you haven't seen yet. And the idea is this is all the science that we're sort of working on right now, right? There's a lot of it, and it's very interesting. And if some of you come down to the American Museum of Natural History and do the RU program this summer, please apply. Obviously, we can't accept everyone, but we'd love to if we can. At least find as many people as possible do stuff. And the next talk is basically about this line: artificial intelligence and machine learning adapted to these E+A galaxies. Okay, so with that, I will then turn the microphone over to Leah, who will then talk about the stuff that she's got. So she's got her own PowerPoint, and she has her own microphone, so I'm just going to walk away with this one.
Can you guys hear me okay? So I'm Leah Voytovich. I'm an undergraduate at the University of Pennsylvania, and I had the pleasure of working with Dr. Liu over the summer on E+A Galaxies. So today I'll be talking about applying machine learning to classifying E+A galaxies. So what is machine learning? Essentially, it's feeding a machine a very large amount of data and having the machine learn from this data. And it's analogous to how humans learn from sensory input data, and they recognize patterns in this data. Machines basically have access to a lot of data and analyze it and recognize patterns, and from this kind of learning, they're able to predict and make certain classifications. And so there are various different types of machine learning, and the approach we took was kind of the most standard type, which is supervised learning. And before I get into our E+A classifier, I just wanted to demonstrate kind of how powerful machine learning really is. So let's say we wanted to make a graph of Albert Einstein's music preferences. So here would be our graph, where each data point represents a song, and the data point would be green if Albert Einstein enjoys listening to the song, and red if he does not like the song. And our axes would be beats per minute, so kind of how fast the song is going, and intensity, or like the loudness of the song. So from the data provided, we can see that it looks like he enjoys songs that are more faster paced and louder, and maybe dislikes songs that are slower and quieter. Okay, now let's say we're given one more song represented by the black data point. Would someone like to try to predict whether Albert Einstein would enjoy or not enjoy this song? Anyone like to volunteer? Go for it.
I think he would like it.
Why do you say that?
Because there's a bunch of green around it, and it's farther from the red.
Yeah, absolutely. So you are in fact correct. He does enjoy this song. This is because we as humans, we can tell right away that there are two clusters going on here. There's the sort of green cluster and the red cluster, and the data point that was unknown falls very, very nicely within the green cluster. So it's really easy for us to say with reasonable confidence that Albert Einstein's probably going to like that song. But now what if I give you this data point? Raise your hand if you think that he would like this song. How about not like this song? Interesting. Okay, so definitely more people. Does someone want to explain why you think he would not like this song? Go for it.
Because there is a red dot to its right and a red dot above it.
Sure, okay. Okay, so that's very intuitive. I will say that this example is much more difficult to predict than the one before. And this is because it's sort of in an ambiguous location. It's not very obviously in one cluster or the other one. And as humans, even though you guys did a really great job, I didn't think that, that you would predict it. But as humans, it's a lot harder for us to kind of make this prediction. But a computer has no trouble doing this. And a computer can use a vast variety of machine learning algorithms to solve these sort of ambiguous and challenging problems. In this case, it uses something called the k-nearest neighbors algorithm, where essentially it draws a circle around the unknown data point and expands the circle until an uneven number of elements from different clusters exist within the circle. And then the cluster that is more represented in the circle is the winning cluster. So in this case, there are more red dots in the circle than green dots, so you are in fact correct that he does not like the song. However, this is a two-dimensional example, and even this was pretty challenging for us to classify. Now imagine if you had 5 dimensions or hundreds of dimensions. As humans, it's very difficult for us to conceptualize the relationships among these data points, let alone make predictions about them. And that's why machine learning is a very, very powerful tool, because it implements all of these algorithms to make these predictions for us. And machine learning happens to be an excellent tool for astrophysics research specifically, because machine learning thrives on having an enormous amount of data. The more data you have, likely the more accurate your model will be. And one of the challenges of machine learning, especially in industries, is acquiring enough high-quality data. And in astrophysics, we have too much data that surpasses the human's ability to analyze it. So these fields go very well together. All right, so the first approach we took to creating an E+A classifier was using supervised learning and binary data. So essentially, we input into the machine a vector of binary values of zeros and ones, where each 0 and 1 represents one of the categorizations that Dr. Lee talked about of an E+A galaxy, where 0 means like the absence of a particular trait and 1 means the presence of such a trait. And then the output is also just a 0 and 1, where 0 means it's not an E+A, or the machine predicts that the object you fed it was not an E+A galaxy, and 1 would be that it is an E+A galaxy. And so the method that we used were decision trees, and we actually had 2 models. One is a simple decision tree, and one is a random forest model. So a decision tree essentially is when the machine asks yes or no questions, and through the process of elimination, comes to a conclusion with reasonable certainty. And then a random forest is simply a collection of decision trees, where each decision tree is applied to a random subset of your data set. So this, the figure here is not a decision tree that a machine will use, because a machine does not understand English, and machines can only read zeros and ones. This is a decision tree that we as humans might want to use when we are looking at some object in the SDSS dataset and trying to decide if this is an E+A galaxy or not. So just to walk you through maybe 2 of the steps, we can look at the emission spectrum and see, is there a spike at 4,000 angstroms? If there is not, we say, maybe this is not an E+A. If there is, we might go to the next question and say, are the photometry values within the desired ranges? If they are, we are with reasonable certainty predicting that this is going to be an E+A galaxy. So our results so first let me explain the difference between a trained data set and a test data set. So essentially, the data set that we curated over the summer has about 20,000 objects in it. The training set is about 80% of that of the entire data set, and these 80% values were taken randomly. And the model is trained using only these values. And then the test set is the remaining 20% that the model is not trained on. And then later, when we feed the model this data, the model will then predict only based on what it learned from the training set. And so,
Question.
yeah.
In order to train it, someone had to tell it those 20,000 galaxies were E+A or were not.
Yes.
Is that true? So
Yes.
who was the person who made those 20,000 decisions?
So that would be the group of interns at the American Museum of Natural History. Yes. It took quite a lot of time to curate that data set, but yes. And that's a characteristic of supervised learning. And unsupervised learning, you would not have this output data already fed into the model. So our results seem relatively good. Our mean squared error across the board is a little over 2%, mean absolute error is around 5%, and mean squared error is about 15%. However, we cannot trust these results because E+A classification is an example of something called a rare object classification, which is essentially where you're asking a machine to find a needle in a haystack. And this generates a lot of bias because your data set is extremely imbalanced, where your target or minority class is very, very undersampled in your data set. And so as an example of how this can produce artificially high accuracies is, let's say you have a data set such that 2% of the objects are E+A galaxies. So 98% of them are non-E+As. And then you feed it to a model, and your model predicts 100% of them are non-E+A. So your model is essentially useless. It could just be one line of code that's outputting no for every single input you give it. However, this is a model that's technically 98% accurate, because 98% of the classifications are correct, because they are in fact non-E+As. So obviously this is a huge flaw and a very big challenge when it comes to machine learning. So there are several ways to combat this issue, and the approach you want to take really depends a lot on the algorithms that you use. But kind of one example method you can do is called dynamic sampling, which is where essentially you create a data set with an artificial ratio, so you oversample your target class. So let's say instead of having 2% of your objects be E+A galaxies, which might be a bit more realistic, you would have maybe 50% of them be E+A galaxies. And then you slowly train the machine. As the machine learns, you slowly decrease this ratio until it looks a bit more realistic. And this is kind of analogous to human learning as well, because, for example, when we're learning math, we start with very simple tasks and we move on to harder ones. So in the same way, you can't ask the machine to find the needle in a step right away. You kind of train it a little bit first. Okay. So next steps for our E+A galaxy classification task include optimizing the model that we already have. And a lot of this optimization is going to come from investigating ways to combat this issue of superficially high accuracies, and as well as implementing other models using other machine learning methods such as neural networks, and then comparing the results of these models. And also one example of an optimization we've already made, so you generally don't want to use, go ahead. Oh, sorry. Okay. You generally don't want to use only binary data when you're making a model, because this is relatively crude data. If you have actual values you could use for certain fields instead of zeros and ones, you should use those values. So for example, some of our fields were photometric values, so we would use the actual values instead of ones or zeros to designate whether they fall within desired ranges or not. Finally, I just wanted to thank Dr. Liu and my peers at the American Museum of Natural History. We all worked on this together, and with that, thank you for listening.
Would you have been able to use like a simulated data set to feed it?
So yes, you can. That's one of the ways that a lot of people approach machine learning tasks, because acquiring data is very, very inefficient. Putting it together yourself can be very inefficient. However, when you create synthetic data, a lot of the times your results don't mirror realistic results. And you can never be sure whether they're realistic or not, because if you're creating your own data, it might not mirror reality quite as well. So there's always risks involved. However, if you don't have time to curate like a 20,000 object data set, I think cleverly implementing your own synthetic data is actually a very common way to go. Any other questions?
How might variations in data quality affect your results?
Sorry?
How might variations in data quality, difference in signal to noise, affect your results?
That's a good question. I should look into that more, but definitely noise is always going to be a factor. And the question is really finding the right evaluation metrics to make sure that noise is minimized and taken into account. But yeah. it will always be a factor in your results. Go ahead.
So was your training data set taken from Sloan or from the Sloan spectra?
Yes, so all of the galaxy objects were taken from that spectra, and then we analyzed all of the emission spectrum and photometry values.
But then the goal will be to apply it to MAGA as well, or
Yes.
to run it on the full Sloan, or?
So I think this question is.
Yeah, we're gonna run on all of MAGA,
Okay.
and then if it works real well, we'll run it on all of Sloan. That's our hope.
How does MAGA? I don't know.
MAGA's gonna be 10,000 galaxies
Oh, okay.
in the end, but of course, full Sloan is like close to 1 million, so that would be really fun. The problem is, of course, Sloan only has spectra in the central 3 arc seconds.
Right.
So even if we find them, we might get some false positives. But as Leah was saying, we don't mind a few false positives, as long as we don't have any false negatives.
So I have one question. As far as I could tell, you were setting up the problem as you know that there's this category of unusual E+A galaxies and you want to find them.
Mhm.
But this sort of machine learning should also lend itself to letting the computer classify the galaxies, right?
Yes.
Why not just throw out Mr. Hubble and Sandage and everybody else and say, okay, I have 20,000 galaxies. Let's just see what the computer thinks is the natural classification.
So that
Have
would.
you tried that, or is there some thoughts about trying that?
Yes, so that would be an example of unsupervised learning,
Right.
which is a little bit less direct of a method, because you essentially have to monitor like the computer's progress and seeing how accurate, like at each stage, is classifying these galaxies. But the goal of supervised learning is you basically, just with enough experience, it should be able to make these classifications. Just based on its knowledge of other data, of other galaxy objects.
And let me mention to you, Phil, that generally speaking, people have tried unsupervised learning to do galaxy classifications a lot. For example, principal component analysis. There was a poster that was talking about that a little bit, how to get principal components, or maybe about merging galaxies and try to compare them in interesting ways. So that is ongoing. This is a particular application where we're trying to do something really particular and special and unusual. But you're completely right. That is a hot topic, shall we say.
Okay. Good. Thank you, Leah and Charles.
Final comments, information to say?
That finishes
Our formal thing, right?
formal thing for the day, right?
Right, now 4:45, pizza's gonna be, but just,
Just do a little.
yeah, do a little summary, and then I'll say something.
Okay, great. So that is kind of the end of our formal program.